this lecture we shall see how neural networks can be used to approximate a function. Also we shall see how a neural network can be used to solve inverse kinematics of a robot manipulator and how to generate a trajectory given initial and final conditions. So, artificial neural network is depicted in this picture. So, it has 3 layers. One is the input layer, the middle one is the hidden layer, and the last one is the output layer. So, for example, here x1, x2, x3, x4 these are the inputs and y1, y2 are the outputs. 4 inputs and 2 outputs are given in this artificial neural network, and there are 3 hidden neurons. So, here in general let us consider x1, x2, xn n inputs and there are L hidden neurons and y1, y2, ym are m outputs. So, the input and the hidden layer are connected by the weights given by uij. So, in this picture we can see that the first input x1 is connected with the first hidden layer by the weight say u11, and with the second hidden neurons it is u12, the weight is given by this, and the fourth input with the first hidden layer we say that it is u41. So, similarly the hidden layer, first hidden layer with the first output is connected by the weight v11 and then it is v12 with the second output. So, in this manner they are connected and they are the calculation, the value of the hidden neurons, jth hidden neurons is calculated by the function sigmoid function sigma of the summation uij xi. So, that is the value of the h1. So, for example, we multiply x1 with u11 and x2 with u21, x3 with u31 etc. So, the summation of u I j xj xi, I is equal to 1 to n. So, this gives the summation the value hj h1. So, here it is x1 ui1. So, this value is h1. Similarly, h2 h3 can be calculated. Then this it is a real value and it is operated with the function sigma, where the sigma function is given by this expression. Sigma of any real number z is 1 by 1 plus e to the power minus z is the value. So, this is one type of sigmoid function, the transfer function, but there are several types of transfer function which can be used in a artificial neural network. For example, y is equal to x, it is an increasing function, the value is between minus 1 and plus 1 in this region and it is constant elsewhere. We consider the interval from minus 1 to plus 1 and the remaining values are constant. Similarly, the function 1 by 1 plus e to the power minus z, the graph of the function can be easily seen that it varies from the value 0 to 1. It is an increasing function and it's when x is infinity it is the value is 1 and when x is 0 the value is half and when x is minus infinity the value is 0. So, it is a increasing function and between 0 and 1. Other functions are given by f of s is given by s by mod s plus a, where a is any constant. So, here also the graph of this function is varying from -1 to +1, and it will look like this. When s is 0, the value is 0, and for infinity it is 1, and when s is minus infinity it is -1. So, similarly the tan hyperbolic function also will look like this. So, the property of any transfer function is simply it is an increasing function and it is bounded by two values, either -1 to 1 or 0 to 1. So, this way that is the property of a transfer function, and one such example is this transfer function sigma z 1 by 1 plus e power minus z. So, the value of the hidden neurons is calculated by this expression. Then we get the output. The kth output yk is calculated by multiplying with the weight vjk of the hj value. So, j varies from 1 to L of vjk into sigma hj is given by this expression. So, for a given input x1, x2, xn, we get the corresponding output y1, y2, ym using this artificial neural network. So, instead of writing using the summation, we can write them in the matrix form like this. If capital U is the matrix Uij and capital V is the matrix Vjk, the elements are given by this thing, and L rows and M columns as given here. Then the expression capital Y means y1, y2, ym transpose, the column vector is calculated by V transpose sigma of U transpose x, where x is this vector. So, the same expression 2 in the matrix notation is given in the form 3 for simplicity. Now, the artificial neural network has a interesting property that any given function f of n variables from Rn and its value is in Rm, it can be approximated by a neural network as given in the equation 3 in the previous slide. So, we can find suitable weights, weight matrices capital U and capital V in such a way that the function f of x and the neural network, the norm of the difference between fx and y is less than epsilon for any given epsilon. So, the property is like this: for if f of x is a given function of n variable, then we can find a neural network in the form of y as given here in the equation 3 or in the equation 2, such that the difference between the function f of x and the neural network is as small as possible. Whatever be the given epsilon, we can find the weight matrices U and V. So, this is a very nice approximation property of any given function. So, to find the weights, what we can do is we take this as the error. The difference f of x minus y norm square is the error defined, which is a function of U and V. Now, by minimizing this error, we get the values of the matrices U and V. Once we obtain the matrices U and V by minimizing this error, we can substitute in the equation 3 this expression, which gives the approximate value of the function f of x. So, to minimize the error, we use the gradient descent iteration as follows. The r plus 1th iteration is depending on the rth iteration minus some small value which is called the learning rate alpha multiplied by the gradient of the expression u, where du is defined by this expression. The rth stage, rth iteration, the du is defined by the partial derivative del E by del u I j. I varies from this thing, because E is the error which is a function of u and v, where u and v are having the elements u I j and v j k as shown in the previous slide. So, E is a function of all this u I j and v j k, and the partial derivatives, these are all the matrices. Du is also a matrix and capital E is a matrix, and its derivative of a matrix means we have to differentiate at each element. Okay. Similarly, V r plus 1, the value of V at the r plus 1th iteration is given by this formula, similar to this thing. Initializing the weights, that is u 0 at the initial this thing, we take the matrix 0 matrix only as the initialization in this algorithm. Then from that we can get one by one, and finally as r tends to infinity, this will converge to a suitable weight which is required. So, that is the standard procedure of the artificial neural network. So, let us consider a simple problem, that is one input x and two neurons and only one output y. So, y can be calculated by this thing, one input and connected by two neurons connected by one output. X is input, y is output, and this is hidden layer 1 and 2. So, we have the weight here u1 and u2, this is v1 and v2. So, v1 into sigma of u1 x plus v2 into sigma of u2 x is the calculation of the neural network. And if we want to approximate this constant a using a neural network, the error is the constant minus the neural network y as given here, the square of the error. To minimize that, so when we substitute y, we will get E equal to a minus this whole square, and sigma of z is taken as the transfer function, the sigmoid function, and so error is written in terms of the sigmoid function like this, del E by del V1, del E by del W1 is like this, the partial derivative of this expression E, where n is nothing but this bracket, square bracket expression. So, now similarly del E by del V2 and del E by del W2 can be calculated in the same manner. So, for example, let x is 2 and the output is 5. We want to find a neural network for relating this 2 and 5. So, we write the neural network, and it has to be like this. We want that 5 should be in this particular manner. So, how to calculate this V1, V2, W1, W2 etc. using the algorithm. So, initialize the weights to be V1, V2 is 0, 0 and U1, U2 is also 0 initial weights. Then the first iteration is denoted by 1 here in the superfix. Alpha is the learning rate is taken as 0.1, and the value is 2 times n. N is when we substitute V1, V2 0, everything is 0 here in this y expression. So, we get 5 minus 0, actual value minus the neural network value at the 0th iteration is 0 here, and when we calculate that del E by del V1 etc., it is coming out to be like this by substituting the 0 values. So, what we get here is the total value, the first iteration gives that V1 is this, V2 is this, and U1, U2 are 0, 0. Now, the second iteration similarly can be calculated. At second iteration, the first iteration value minus alpha and 2 times the n value is this, and the derivatives, partial derivatives are given by this when we substitute the first iteration values. So, it gives the second iteration values to be like this. Now, if you substitute V1, V2 and U1, U2 in the neural network formula, we get the value close to 3. So, we see that it has improved slightly. The value of the neural network is coming towards the required value 5. So, proceeding like this for the third, fourth iteration, we can easily see that the value of the neural network will converge towards 5, and it will be as closely as possible we can find the weights suitably. Now, if f of x is a given function, so earlier we have seen how a constant output is approximated by a neural network. Now, if a function f of x is given in the interval 0 to 1, how to approximate it using a neural network. So, let us divide the interval by 0, 0.1, 0.2 etc. up to 1, the given interval, and so the square of the x square is given by 0.01 and 0.04 etc. 0.81. So, the square of these values are given here in this bracket, and so if you denote xk to be 0.1 into k, that is given by this interval, and the value alpha k, the required values are actually the square of these values, these are the required values. Now, if you define the neural network for any value of x to be in this particular manner, here we are considering one input, again we consider 5 hidden neurons in this case, and then one output, all of them together it is one output. So, this is x and the value is y of x, and the calculation of the hidden neuron are given by this thing, where sigma of z is taken to be 1 by 1 plus e power minus z as given in the previous one. Now, if we in the place of x, if we substitute the partition values 0.1, 0.2 etc. for xk, we can calculate for each value of the partition the corresponding neural network value is given by this one. So, if we suitably find this weights v I and u I equal to 1, 2, 3 up to 5, then so what is the requirement here? For each partition value, the value ak is given by 0.1 square k square for k equal to 1, 2, 3 up to 10, and neural network values are given by the previous formula as given in this one. So, the difference between the required value alpha k and the neural network, the square, should be minimized at each and every partition point. So, error is summation k equal to 1 to 10 of the actual required value minus the neural network value whole square at each partition. So, if you minimize this one using the gradient descent method as shown previously, we can easily obtain all the weight values. Now, if you substitute the converged value of the weights, we get the function approximation, that is f of x is approximated by the function y of x by substituting the values which we obtain after many iterations of the artificial neural network algorithm. Okay. So, this can be this is a function approximation using neural network. It is a simple example. So, this procedure can be applied to solve inverse kinematics for any robot manipulator. So, for example, the simple robot manipulator which we consider is the 2 link manipulator, where theta 1 and theta 2 are the joint angles and x1 x2 are the end effector positions. So, x1 is given by this and x2 is given by this one, where L1 is the link length. First link is L1 and second link length is L2. So, we can easily solve the inverse kinematics. We can find theta 1 and theta 2 in terms of x1 and x2 very easily, which we have seen in the previous lectures. But how to use the artificial neural network for finding the inverse kinematics solution is the following. So, let us consider the neural network value of theta k where k is 1 to 2, theta 1 n and theta 2 n is calculated by this neural network. So, let us consider the input is here x1 x2 and we consider hidden layers. There are L hidden layers and we can connect the L hidden layers and with this, and the output are given by this thing, 2 outputs theta 1 and theta 2 are the outputs for this problem. So, this is coming out of the neural network, therefore, we denote it by theta 1 n and theta 2 n. So, after finding suitable weights V I and W I, when we substitute this theta, the neural network values of theta should be very close to the actual inverse kinematic solutions of the problem. So, how to find the weights properly, that is what we want to see. Now, when we initialize the weights arbitrarily, let us say all the weights are 0 in the beginning, then we can substitute in the neural network and then obtain the theta values theta k n. Then substitute in this formula, in the place of actual value of theta we substitute neural network value of theta and obtain the neural network value of the x1 and x2. Then we subtract the given value of x1 x2 minus the neural network value whole square. So, this should be minimized, E should be minimized suitably, so that we get Vi and Ui values, the weight values after convergence of the neural network algorithm. So, the error is given by this expression, and using the greatest descent procedure algorithm we can obtain the weights suitably, and we get the after getting the final weights we substitute in this particular formula again. So, whatever is coming out to be the neural network value, that will be the actual value of the theta 1 and theta 2, the inverse kinematic solutions of the problem. So, this procedure can be adopted for any type of robot manipulator, and for illustration purpose we have taken the simplest form of this one. So, what we did here is we have x1, here it is written end effector position, and these weights are connected by uij. These are the hidden layer. Using the sigmoid function we calculate the theta 1 n and theta 2 n. So, these are the neural network output. So, once we get the joint angles using neural network, we can again calculate from here x1 n and x2 n using the same formula. Then this will be taken back to this expression. The error is calculated, the error is summation x I minus x I n whole square, I is equal to 1 to 2. So, this is minimized. So, every time we get the inputs as x1 and let us say x2, and we get x1n and x2n and subtract and square it, we minimize this expression to get the new weights. So, every iteration we get a weight and put it here, they keep on repeating, finally it will be converging to a required weight. So, that is a procedure. Now, we can also generate the trajectories, because we have seen in the biped robot manipulator the ankle trajectory is there as hip trajectory. So, various trajectories are to be generated using polynomial. So, if there are let us say 4 constraints given, initial condition, initial velocity and final position and final velocity are given for a particular trajectory, then we can write a third degree polynomial and then we can find the coefficient of the polynomial using boundary conditions. So, instead of that we can also write in this particular form. At here t0 denote the initial time, tf denote the final time, and so what it shows here is at t equal to t0 the value is this bracket will vanish. So, now if our condition is the ankle's trajectory at t naught is given as some value, let us say x naught, and x a at t naught its derivative, the velocity is given to be 0, let us say, and similarly x a t f is given to be x f and the velocity t f is some value, for example 0. So, if the initial position, velocity, final position, final velocity are given for 4 conditions are given, then we can generate a trajectory using a neural network. So, the neural network can be written as given in the previous slide. Here the time is the input, t is the input and the value of the neural network is the output, and let us say any number of neuron we can consider. So, the selection of the number of neuron in the hidden layer is left to the user here. So, normally for this type of problem we can consider one input, we can take 3 or 4 hidden neurons and one output is given. So, the value of the neural network after calculating the formula as given in the equation 3 is the value of the n1 for this particular input, t is the input. So, now if we consider t equal to t0, the first bracket is not there and here we have some constant value tf minus t. So, our aim here is only to train this N2, the neural network 2 for this particular value, that is xa at t naught equal to x naught. So, when we substitute in the first formula xa at t naught, that is nothing but tf minus t naught whole square, that is 1, and only the n2 will come, n2 of t naught u2 and v2. The weight matrices u2 and v2 should be calculated for this particular value, where the output of the neural network is given by xa of t naught, which is equal to x naught. That value should be taken, and for this output we should find the weights u2 and v2. That is the meaning. Similarly, we should differentiate this first equation xa dot t. So, when we differentiate we will get some expression from the second term only, because when we substitute t naught after derivative also the first term vanishes, only the second term will remain. So, in the second term the value of the output is 0 when we differentiate x a dot at t naught is 0. Now, after differentiating this 2 times this bracket multiplied by the neural network etc., and then when we substitute t equal to t naught, we will get some constant value multiplied by the neural network. So, our aim is to adjust the weights of the neural network for these two conditions, because in the first condition also the neural network comes, in the second also we will get some bracket into the neural network. So, the neural network should be trained in such a way that it satisfies these two conditions, and the weights are calculated using the iterative method, because the outputs are given and the U2 and V2 should be calculated. Similarly, for training this N1 neural network, we substitute the final time Tf. When we substitute final time Tf in the place of t, we get the second term is 0, only the first term will survive. Similarly, when we differentiate it and then substitute t equal to Tf, the second term will become 0, only first term will remain. So, using these two conditions as output, we should train the neural network 1 N1 for finding the weights U1 and V1. Once we find U1, V1, U2, V2 using the iterative methods, we substitute, we get the entire trajectory for all values of t. For training we will use only 2 time instances, that is t equal to t0 for training N2 and t equal to Tf for training N1. So, after getting all the weights we substitute here, that is useful for finding the trajectory for all values of t. So, similarly, if we increase the number of conditions, instead of initial and final, we also have 2 conditions at the middle, that is height of the trajectory path as well as the velocity at this path, the derivative. Then we can write the neural network in this particular form. 3 neural networks can be considered, and by substituting the 3 time instances, we can train according to the output values the 3 neural networks, and then substitute the weights here. We get the trajectory xa of t for the 6 constraints. So, depending on the number of constraints, we can write the neural network expression, and this can be utilized as the trajectory for the biped robot walking. Instead of the polynomial trajectory, this can be also utilized. So, here, so in this lecture we have seen how to utilize the neural networks for finding the inverse kinematics solutions for a robot manipulator, as well as how to generate various trajectories for biped robot manipulators. Okay, thank you.